the next presentation will be made by Professor Abdelkarim Haddad from the University of Delhi. And the title is MOC Application Design of Supersonic Nozzle, its comparison to computational fluid dynamic analysis. So, Professor, you have
Thank you. Thank you. I'm standing for one of my students, in fact, and the student has been ill for these last days, and she didn't. She's not able to come. Now I'm standing for her. This is the work of my students, not mine. Right. So I will be talking about the method of characteristics that is applied for the design of supersonic nozzles, and then with the results that we'll take from the method of characteristics, the results obtained will be compared to the computational fluid dynamics analysis. The contents of my talk will be divided in five sections: introduction, nozzle design, how the nozzle has been designed using the method of characteristics. The method of characteristics is one of the methods that kind of transforms the partial derivative equations, the partial differential equation, into total differential equations, and then we can transform them into finite difference, and then move to design or develop a computer program based on the method of characteristics. And then we apply the ANSYS fluent computational dynamics. And the results obtained are compared, and we'll discuss and finish by conclusion. Aerospace propulsion, which is our theme and our application, is essentially based on propulsion engines. And one of the parts of the propulsion engine is the nozzle. The nozzle is, in this case, the supersonic nozzle, which are also called the de Laval nozzle, in honor of the French engineer de Laval. These are the part that would give the propulsion. These nozzles convert pressure into energy, into kinetic energy. They expand the flow from very low velocity to very high velocities that can go to hypersonic, Mach 5, Mach 10. These last days we see Mach 15. This is quite a lot. This hypersonic is very highly compressible flows. And also they are used to control the expansion. Our study will involve the design of contoured nozzle. Contoured nozzle means that the bell-shaped nozzle, there are different sorts of nozzles, they have different geometries, and the bell shape is one of the best, in my view, that is actually using the method of characteristics. We'll be also using the computational fluid dynamics. We'll be taking the nozzle that we have designed using the method of characteristics, and we'll compare the two results. This is nozzle design. The nozzle design is done using the method of characteristics. We have here the stations, what's called in fact, the method of characteristics is a very good method because it does apply the conservation equations, which are partial differential equations, and then that move them to two equations, in fact, which are total differential equations, and then make the calculations. So the computations are real, and the calculations are not done anywhere. They are done along what's called the characteristics, which comes from the name of method of characteristics. And the characteristics in this case is the Mach line, which comes from the Ernest Mach. In his honor, we know the number of Mach, the number of the German in the Second World War. And these are the characteristics along which the properties are calculated. Properties like pressure, velocity, and we are here in two dimensions of this, so the velocity in x and y, the temperature, the pressure, the density, anything we can calculate. And to do that, we have to include a geometry. This is the bell geometry, the bell-shaped geometry. What we do in bell geometry, we divide the bell-shaped geometry into two. This is the throat. The throat is constituted of two arcs of circles of different radius of curvature, and then the bell shape is simulated by a second-order polynomial. So this idea of second-order polynomials has been first developed by somebody in Purdue University in the United States, in the US of A. This guy is called Hoffman, Professor Hoffman, and there's another guy working with him, Professor Zucchero. Professor Zucchero has passed away some time ago, and then Professor Hoffman is in the Purdue University. So this is the simulation of the geometry that we have to take and put into the computer program. We have also the conversion part. This is the from x equals 0 until the end. This is the supersonic part, and then we have here the transonic part, which might equal 1, and then before that we have the conversion section, which is this. This is the conversion section. The subsonic part marked less than 1, and from here and to there, in this region, we'll have the combustion chamber. This conversion part is also designed using a method that has been developed by somebody, an American from India, an American from Indian origins, which is called Rao. And this is an experimental method. There is no experimental method that has been developed after many experimentation. This guy, Rao, is quite known in rocket propulsion, very known in rocket propulsion, has developed this method. And we are using this method that has been used by Yuki in 2018. Rao has developed this method something like 1960, a long time ago. And we have using this to design it. And then the two parts, the conversion part and diversion part, will form our nozzle. Yeah. This is the design of the nozzle using the method of characteristics. This is done. We can use method of characteristics. We have developed a program in Fortran that solves the differential equations. We have results from the method of characteristics. All right. Then we have this design. We take design and put it into Fluent. This is the computational fluid dynamics analysis. What we have done in the analysis, it is axisymmetric. We have symmetry. It is in 2 dimensions. See, if it is axisymmetric, it's in dimension. Using the Fluent, if you put on axisymmetric, he automatically takes the 2 dimension. Using Fluent software, we have told the computer program that we'll be using the 3 conservation equations, the conservation of mass, continuity equation, the conservation of momentum, the Navier-Stokes equations, and the conservation of energy, which comes from the first law of thermodynamics. If we take these 3 conservation equations, we cannot close the equations. The system is open, so we have to close it. We have to add 2 other equations, and the 2 other equations are coming from the turbulence. And in this case, and from our humble experience, we know that the K omega, the model of K omega SST, is one of the best in this case. So we have applied the model of the 2-equation model of turbulence, K omega SST, which is production and dissipation of turbulence, the production of turbulence energy and the kinetic turbulence energy, is omega. The K omega SST is just 2 words. It's something. It's kind of something that has linked the K epsilon method, quite known and developed by somebody from the United Kingdom, from England. Professor from I think from Cambridge University, and the K omega model. There are problems with K omega and the K epsilon, so that they link them together. That needs time to explain, but they link them together, so these 2, so that the positive thing of the K epsilon has been used, and the positive thing for K omega is used, and they called it the K omega model. We have used axisymmetric, no time, permanent, viscous with compressibility effects, density based. We have used air, just for simulation, perfect gas, and we have used a residual, which is the sensitivity, which is 10⁻⁶, which is quite good number. Right. We have developed also the mesh. The mesh was something of consisting of 8,000 elements, which is not a lot, but they do the job. We have 8,000 elements, but we have refined the mesh near the wall and at the throat. Why? Near the wall we have the viscosity effects. The viscosity effects are strong effects, so we have to refine our mesh. And near at the throat, because the property gradients from one station to another station, the property gradients are very high, so we have to refine. Doing this, we run the two programs and we got the results. These are the results. I have two results here. I have the pressure versus the length x. I'm working here in non-dimensional parameters. This is along the center line. This is along the wall, near the wall. We can see that near the wall, the pressure dropped very highly. It's dropping here from 0.5, something like 0.5, and then stabilizing afterwards. In this case, we have a drop of the pressure, of course, because if you drop the pressure, the velocity will be higher, and then the Mach number will be higher. That's what we are expanding the flow. And the blue is the results coming from the method characteristics, and something like red or something like that, coming from the finite volume method. Finite volume method is the one applied by the fluent. What we see here, that there is a point of discontinuity here that can be sensed by the method of characteristics, but the other method cannot see it. This point A comes in fact from a discontinuity, that we know that there is a discontinuity. Discontinuity basically see here, the point A. The point A is the attachment point that attaches the throat to the supersonic section. We know that there is a discontinuity here. So the method characteristic, this is one of the main characteristics of this method. It can sense the discontinuities, point H. This one cannot do it. And near the wall, they can't sense that. This is for the pressure. We can also see the contours, and we have here the contours of the pressure, of the Mach number. We can see the Mach number is coming high and high. That's because the flow is expanding, the air is expanding, there's expansion, very high expansion. We start here for Mach equal 1 until Mach equal, I don't know, Mach equal 3 point something, more than 3. Which is something like 2,000 meters per second, I think. Here also, this is blue, but we cannot see there are here some kind of difference blues. We cannot see them in the picture. The pressure here is high, and then less, more expensive. If the pressure is diminishing, then the Mach number in the continuous point will be higher. Oh, sorry. We have made also, my student made, I haven't made it. We have made also a comparison in terms of performance parameters. The performance parameters mainly are the thrust, the mass flow rate. We cannot say that the mass flow rate is a performance parameter. The main performance parameters are the thrust coefficient, the effective velocity, and the specific impulse. We can see that the two methods here are within something like 3%, the maximum 3%. You can see it is less than 1% of the error, which leads us to say that the two methods can solve the problem of the expansion in supersonic flows. But the method of characteristics still, even though it is simple, but still, in my view, still is the best method, because it can sense the differences. It can sense the discontinuities. The other one cannot sense the discontinuities. We know why. That's the main thing my PhD student has done. And in conclusion, we say that the present study compares the two methods, method characteristic and methods of finite volume fluent. Both methods produced comparable results in terms of pressure and Mach number, which are the main parameters. The performance parameters showed similar outcomes in both, even though the method characteristics can sense the flow better than the finite volume method. A key advantage of the method characteristic resides in its ability to design a supersonic section profile based on a desired exit Mach number. That means that if we know the Mach number of the outlet, we can design the supersonic nozzle just on the basis of the Mach number at the exit. Thank you. I have been very quick because time is short. Thank you and for your patient listening. And if any question, I will be happy.
Thank you very much, Mr. Haddad, for very interesting presentation. So now, of course, if any question, please go. Always you. No problem. I have no problem.
Just to say, for your presentation, I have queries. Just curious question. Is regarding the effect of the tip clearance on this? Tip clearance. The tip clearance is defined the distance between the blade of the rotor and the casing of the nozzle. If we can introduce the effect of the tip clearance
in nozzle there are no blades.
Yes.
There is no clearance. There are no blades. Yeah. There are never have been blades in nozzle. Whether the nozzles are subsonic or supersonic, there are no blades. The nozzles are the flow coming from the combustion chamber will come with a high thermal energy. This thermal energy is taken into account and transformed into kinetic energy, into velocity, without anything. Just the geometry of the configuration of the nozzle will control the expansions.
Any other questions? So, thank you very much.
Thank you.
You have questions? After this, Professor, maybe we have to finish first all the presentation before we move forward. There is another one. If there is no Ben Hassin, it will be lunch. So it's up to Ben Hassin. Okay, thank you. So.